A short time ago, an American airplane dropped one bomb on Hiroshima and destroyed its usefulness to the enemy. That bomb has more power than 20,000 tons of TNT.
Okay, in this video we will be detailing the procedures for difference of two sample means t-statistic significance test. To demonstrate these procedures, we chose to analyze the question, which metal is better at shielding beta radiation from thorium-234? Our null hypothesis is that the radiation that passes through the tungsten is the same amount as the radiation that passes through the aluminum. Our alternative hypothesis is that the radiation that passes through the tungsten is less than the radiation that passes through the aluminum, because according to our previous knowledge, we believe that because tungsten is heavier and a denser material, it should be able to repel more of the radiation than aluminum, which is a lighter and less dense material with less atoms that are in the way of the radiation. So to make this experiment consistent and get rid of confounding variables, we use the same size, same thickness of aluminum and tungsten. The guided counter, which is the detector for the radiation, and the radiation source were both positioned at the same exact place. And so now that we have addressed confounding variables, here are our assumptions: that our sampling was completely random, which it was, and the independence of the observations, of each observation that we were sampling. And also, because our sample size is 15 for each aluminum and tungsten, and there is no strong skewness as detailed in these box plots, tungsten is just about symmetrical and aluminum is only slightly skewed left. We can assume that this data is approximately normal. So therefore, we can go on to do our significance test.
So for our data, we calculated the means, the sample standard error, the mean for tungsten and the sample error for tungsten. We have 38.4 for aluminum, 7.008 being the standard error. We have 23.6 as the mean for tungsten and 5.591 as the standard error. Now these values are all measured in radiation counts per minute as given by the Geiger counter. Now for this experiment, our degrees of freedom is calculated using this formula, and the degrees of freedom are the number of values in the final calculation of the t-statistic that are free to vary. So using the formula that I just showed, our degrees of freedom are 26.683. And since we're assuming a alpha value of 0.05 for this test, we can use that value along with our 26.683 degrees of freedom to get a t-star of 1.704. This is pretty much on a t-distribution like this with 26.683 degrees of freedom. The 95th percentile is 1.704. Now, using this formula, we calculate our actual t-statistic for this test, and that formula is shown here. Substituting in all the values, we obtain a value of 6.394. Now, since this t-statistic is much more extreme than our t-star, we have statistically significant evidence to reject our null hypothesis here. And if we proceed to calculate a p-value for this, we would find that there's only 3.985 times 10 to the negative fifth percent of a chance that the t-statistic will be as extreme as the one that we found. So obviously, since that's such a low probability, we only reject the null hypothesis in this scenario, which means that our null hypothesis is rejected. That means that it's extremely unlikely that such an association would occur simply by chance, and that perhaps there is indeed less of the radiation counts in tungsten than aluminum. And that concludes our video here, so thank you guys for listening and good luck on the final.